Hi guys, Mr. Johnny here. In this video I will show you what many of you actually has been waiting for. It is the schematic for the power supply that I built for this soldering station, which you can see in all its glory. To sum up again, it's a half bridge which outputs 24 volts and handles 3 amps to power the T12 iron. So, the schematic. I have to say straight away that the schematic is hand drawn, so please excuse the crudity of the model. I did not have enough time to paint it or do it in scale. Okay, now it fits all. As you can see, yeah, it's not quite the beginner's project, really. It is quite complex for what it is. I could have done much easier. I could have done a power supply which would do the same thing and would be easier to build, but again, I built that power supply here following two main rules. To make it fit, that's one. And second rule is to use whatever parts I have on hand and not buy any extra. Okay, so let's start from the mains. Mains come in here. You can see live goes through fuse into this interference filter. This capacitors 100 nanofarad 400 volt DC rated capacitors. Better idea would be to put a X2 class capacitor rated for 275 volts if your mains is 240 volts or so. This is a common mode choke. The inductance of a single coil is about 5 millihenry, if memory serves me right. This thing is a choke you see right there. You can see two interference capacitors. Fuse is here in the heat shrink. Then this part is a 2 amp bridge, thermistor and a bulk capacitor. All of which you can see here as well. Bridge, thermistor and a bulk capacitor. For simplicity I used, well, for clarity of the schematic really, I used the nets just like in CAD because, yeah, this schematic is already a mess. It would not help if I were to go and snake these connections all over the place. So that's mains come in. You have rectified mains here. Then you have this half bridge, which is rather simplistic. You have two transistors, switching transistors. They are, in my case, MGE 13009. The transistors you might also use are MGE 13007s. Why did I use 13009s? Second rule, I used whatever I had to hand. You can see this shape in circuit also, with these resistors between collector base, which provide a startup mechanism. So whatever transistor turns on first, conducts first obviously, and kicks the oscillation and starts the oscillation, and then the feedback of this winding, because it's in series with the primary. Whatever transistor turns on, there is current flowing through the primary, so there is current flowing through this feedback winding, so the current is also induced in the other feedback in the base windings, and it springs into oscillation just fine. By the way, the small diodes like this you see around, which are not marked in any way, are 1N4148s. The diodes which are marked are bloody obvious what they are. So this part is rather simplistic. As one thing I gotta mention here is the snubber values. although they work for my case, they might not work for your exact transformer. Again, your mileage may vary. Even let's put it this way, your mileage will vary because the values necessary for the proper snub in action are strictly dependent on the leakage inductance your transformer has, and that varies with how well your transformer is wound. So I guess this section does not really pose much interest anymore. Then you have this common cathode diode. I used MBRF 2200 CT, which is a common cathode diode, contains two 10 amp diodes inside. Both are rated, of course, both 200 volts reverse voltage. Then the output of this rectifier is fed through the choke. In my case it's about 220 microhenry, rated for about 3 amps, into this single capacitor, which is enough. 470 microfarads, 35 volt rated. Has to be a low ESR capacitor, that's why one is enough. Mine is indeed a low ESR capacitor, which you can see from a goldish color and the appropriate marking on it. Right there it says LESR. I'm not sure if you'll be able to catch it. Right there. Anyway. Okay. That's your power transformer, obviously. That's your drive transformer. Drive transformer is wound on this core. Both cores are toroids. In fact, every core in this power supply is a toroid. Common mode choke is on a toroid, drive transformer is on a toroid, power transformer is on a toroid, output inductor is on toroid. So this drive transformer is wound on the core, which consists of two little donuts like this. So the total size is 14 by 8 by 10. Outer diameter, inner diameter, and height. It's not necessary to use a toroid to start with. And even if you use toroid, it's not necessary for you to go and buy two small cores and stack them together. Again, I used whatever I had to hand. That's why I wrote these kind of cross sections, so you can go and find a core which is of a similar cross section. The drive transformer is 30 square millimeters in my case, power transformer 96 square millimeters. The core must have a permeability of around about 2200 in order for it to work right. Yeah, primary of the power transformer is 51 turns, single wire, 0.4 millimeters in diameter. Secondary, 22 turns center tapped, thus 11 in each half, and it is wound using 3.5 millimeter in diameter wires. It's a secondary. As for the drive transformer, all the windings on a drive transformer are wound with 0.5 millimeter wire, and the corresponding number of turns you can see. Primary 40 turns center tapped, base windings 7 turns each, and the feedback winding 2 turns. And as for the controller, it's really a textbook kinda application, except for one little thing. That one little thing is this, is how the overcurrent protection here is done. As you can see, this comparator error amplifier does the voltage regulation. Its inverting input is connected to this divider, which just brings the VREF, which is this pin of the chip, which is 5 volts in half, so that's 2.5 volts here. Then you have this divider, which is connected to your output, right there. And it's set in such a way that when there is about 25 volts on the output, this point is going to be equal to this point. Of course, due to the fact that I used 5% resistors, it is not quite what I expected, but it's good enough. Voltage in my case on the output, loaded or not loaded, it doesn't really change, 25.2 volts, which is alright, especially having considered that I did that modification to a controller, which will prevent the MOSFET from being damaged. Alright, so you can see this error amplifier is easy. But what the hell is this about? You can see non-inverting input is grounded, then inverting input is fed from the divider, again from the VRF, through a 2.2K resistor, and fed into the inverting input. And also this exact node, inverting input, goes through a 2.2K resistor to I-sense. And what is I-sense? I-sense is this point. It's a center tap of the transformer. As you can see, the center tap of the transformer actually does not connect directly to secondary ground. It does so through a low value resistor, 0.1 ohms 2 volt resistor in my case. And why in such fashion? Well, you could go and put the center tap directly to ground and put the resistor from ground to the output, but that way you will have the drop across this resistor excuse me, influencing the voltage regulation capability, because let me actually draw a little sketch so you'll get better what I'm saying. So that's a little sketch. Normally it's done like this. You have the secondary here, same story, but the resistor, current sense resistor, is right here. Your positive output is here, everything is fine, but your negative output is here. It goes through a resistor, but your voltage regulation loop actually monitors the voltage across the capacitor, not the voltage on the across the output, which is V plus V minus. So let's say you have 0.1 ohm here, and you draw 1 amp. Then you will have 0.1 volts dropped across this resistor. Your controller will happily regulate the voltage here to, let's say, exactly 24 volts. But the voltage across V plus V minus is going to be 24 minus this drop, 23.9. In this case it's not severe, but it's still a bit. Again, I'm a picky bastard. This bothered me, so that's why I did it that way. As in this case, you have the low value resistor out from the loop. Your controller, actually, you can see, that's a divider which says the voltage on the output. It goes to positive output into ground, and ground is after this resistor. So this resistor, of course, develops a voltage across it when the same 1 amp flows, let's say, but the polarity is going to be such that this end is going to be negative and this end is going to be positive. And to prevent this, and the way the feedback here works is quite interesting. It's a bit unusual, but it's simple to grasp. So the I-sense, actually, as you can see, during operation swings a little bit below ground, which is this point. At 1 amp it's 0.1 volts below ground, but the way it does is that non-inverting input is grounded, inverting input is lifted above ground by some voltage, which is my case, it's about 450 millivolts, something like that. You can see from this divider, 2.2K to 20 ohm, fed through 2.2K resistor to here, and here into this same node that I-sense signal is mixed, and it is negative. So when the large current flows here through this resistor, it develops such a voltage here that eventually the overall mixed value here, which is about 0.45 volts, is gonna be nulled out. And if that happens, effectively both inputs of the error amplifier are connected to ground, and in that case the inverting input, non-inverting input has kind of priority or whatever. Anyway, with two inputs grounded, with both inverting and non-inverting, the output will go high and will decrease the duty cycle. That's how the current protection works. Now, again, don't worry, I will put a link to the picture, to the steady picture that I'm gonna take in the description. You will see a link to a Google Plus page where you can find this schematic, a picture of it. Yes, you can see I am a bastard here. I did not include the pin numbers on the chip. But the thing is here that if you are a hobbyist, you really should know how to use datasheet. And this is perfectly enough. If you're lazy enough, or I don't want to become an arrogant asshole here, but if you don't get how to use datasheet, you really should not build this kind of circuit. It's a mains fed power supply. It can kill you if you do it wrong. It has the parts of the circuit which are live, and also if you make the transformers or any part of the, if you make the transformer incorrect, in the wrong way, if you make the PCB in the wrong way, if you make some wiring in the wrong way, you can get really hurt or killed. So yeah, not quite the thing what I will recommend to a beginner or any lazy person there is. The pins are labeled, so yeah, you can go and into the datasheet and find which pin does what. Let me say to you straight away that it doesn't matter which error amplifier you will use for the current sense or for the voltage sense. They are equal. They do exactly the same. You can swap them around. Just make sure to use the correct inputs. Do not put non-inverting signal that's supposed to go to the non-inverting input onto the invert. Do not put the signal which is supposed to go to the inverting input onto the non-inverting input. Okay, that's enough. These are again some frequency compensation networks. In my case they are 100K and 10 nanofarads for both error amplifiers. Again, your mileage may vary. You may need a different value. Now, the one interesting feature there is that I encountered and caused me some trouble and a little bit of headache is the fact that the power supply refused to start sometimes. Ooh, sometimes. Yeah. But why it did do that? Well, if you follow this series for a while and you saw one of the first videos in the series, you saw me in early videos demonstrating that the circuit works without the controller, with the primary of this drive transformer in midair, and you saw that when I short out the primary, the oscillation stops. That's a hint for you. Now, let's say you apply power. Voltage here rises. Whatever the transistor here turns on first, starts the oscillation, feedback kicks in, everything is hunky-dory. Well, it should be. Until some voltage appears here, and thus here, and thus here. That voltage is small right now. It is not enough for the chip to be of any use, so imagine the chip non-existent. And imagine these resistors not existent. This 470 ohms. Then what you have, a transistor which is turned on permanently. If the voltage here rises enough to turn it on, the primary of the drive transformer is going to be shorted. And what that enough voltage is, well, has to be a little bit bigger than base emitter junction, drop across this resistor, drop across these two diodes. Why this exact value, 470 ohms? Why this exact value here? Well, this value I chosen because ATX power supply use it, and it works great there. So I decided to follow it. Well, actually they use a little bit lower value, but since in my case it's 24 volts and not 12, I use 2.2, it works fine. It is actually somewhat more complex than picking it out of blue sky like I did. You have to choose this resistor in order for the transistor in the chip to have a correct load in the collector in order to produce nice fast rise and fall times and not exceed the maximum ratings of the currents through that collector. Oh boy, of the current through this transistor. So yeah, 2.2K works, but why for 70 ohms here? If you again look into the datasheet for tl494, you will find that the voltage range there is specified from 7 to 40 volts. So the chip starts working from 7 volts. And let's do a little calculation. What kind of voltage do we need here, or sorry, do we need on the output to turn this transistor off when this chip is sleeping? So you have a divider for 70 ohms and 2.2K, and your output of the divider has to be base emitter junction plus 2 diode drops. So effectively it has to be 3 diode drops, let's say 1.8 volts. Now let's punch in the values of our divider. The bottom resistor is 470 ohms divided by the sum of those values, 2.2K and 470 ohms, so that's 2.670. That's your transfer function of the divider. Now we need this divider to output less than 3 diode drops, roughly 1.8 volts, when the voltage on the output is not enough still to power the controller. So we need the output of the divider to be less than 1.8 volts when the output voltage is less than 7 volts. And if we multiply this transfer function by 7 volts, we see that at that point the controller will start operating right now at 7 volts on the output, but the transistors are still gonna be off because the voltage on the output of the divider is going to be 1.23 volts, which is not enough to turn these transistors on. I hope that explained it a little bit. Oh yeah. Yeah, I think that will be enough. It's 25 minutes already. I touched on every subject I wanted to touch. I touched on a current sense. I touched on why exactly those resistors that I added in one of the later videos in the series helped to make this in reliable. So that's that. Yeah. What else? You can see also, let me touch quickly on this. When this transistor turns on, it shows it puts effectively, it pulls the base of this transistor, which drives the which is connected to the primary of a drive transformer, to ground, while its emitter is actually lifted above ground, so it's turned on properly. And when the dead time is between those output pulses, both transistors here are off, so they are not existent again. So during operation, you have to make sure that these transistors are off. And how do you do that? Well, you short the primary. Just like I told you before, when the voltage here is lower than 7 volts, these transistors cannot be on. But when the output is higher, it's regulating at 24 volts or roundabouts, there is plenty enough voltage on the output of the divider to turn this transistor on and this transistor on when the chip wants the dead time to be active. So both transistors turn on, effectively shorting the primary out and killing off the oscillation for a short period of time. But because the capacitor retains the charge, after the dead time is that little time that the dead that little moment that dead time takes is not enough for the output voltage to sag down so much that the controller will switch off again. I'm making it unnecessarily complex already. I'm gonna take a picture and call it quits. Any road. Thanks for watching. See ya.